Okay, so today we're going to be talking about electron configurations and then noble gas configurations. All right, so things that we need to know before we go into that are some information about the periodic table and about the structure of the atom. So we're going to use the Bohr model here. Again, it's not the most updated model, but it's just the model that we're using so we can understand it. Okay, so if I've got my nucleus, this is my nucleus, all right? And then I've got these rings. The first level, okay, has two electrons in it. The second level has 8 and so on. Okay, so I'm going to just draw them in. So you can see that there's these different energy levels. Okay, these are called energy levels, and they're actually represented on the periodic table by each period. So each period on the periodic table represents a different shell, a different energy level. Okay, so there are a total of 7 energy levels that we know about right now. The group designates the number of valence electrons. Remember, valence electrons are those ones in the outside shell only, not the ones on the inside. The inside ones are called the core electrons. The outside level are called the valence electrons. Okay, so when we look at our periodic table, we can count the number of valence electrons, and that goes up to 8. Okay, that goes up to 8. When we look at our periodic table, remember our valence electrons, there's going to be 1, 2, skip over your transition elements, 3, 4, 5, 6, 7, 8 valence electrons, okay? The period is each energy level, each shell, okay? Some things that you're going to need to know are going to be the orbitals. There are 4 orbitals. There's an S, a P, a D, and an F orbital, okay? The S orbital comes with these elements right here. Those are the S orbital. The P and this block right here where the 2 is, where this empty space is, that's actually going to be helium. So pretend helium is way over here. That's also an S orbital. The P orbital can hold 6 electrons, and it's right here. These 6 rows. Okay, B, C, N, O, F, N, E. Remember, S holds 2 electrons. Okay. The D orbital is going to be your transition metals, and you'll notice that there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that your D holds 10 electrons. And your F is going to be the lanthanide and the actinide series down here. Those are going to be your F. Okay? Those are going to hold 14 valence electrons. Okay? So those are going to be very helpful for us, the S, P, D, and F, in determining and writing out our electron configuration. Just so you guys get an idea of what the orbitals look like, the S orbital is a sphere like this. This is the S orbital. A P orbital is kind of like a figure 8. There are 2 lobes that the electrons are in. A D orbital is like a little bit more complicated. It's like 2 bow ties. And then the F orbital looks like this, and you can see how complicated that one is. There's 1, 2, 3, 4, 5, 6, 7, 2 electrons in each lobe. Okay, each lobe has 2 electrons in it. Okay, so that's your S, your P, your D, and your F orbitals. We'll see them one more time on our periodic table. All right, so I just wanted to review. We've got our S orbital, the first 2 groups. We've got our P orbital holding 6 electrons, groups 3 through 8. And then we've got our D orbital, which is our transition metals, and then our F orbital as our lanthanide and actinide series. Make sure you redraw this in your notes. All right, so we're going to try our first electron configuration. And the way that we're going to do this, we're going to start, I'll write the electron configuration just for helium. Okay, so this is helium right here. What I'm going to do is I'm going to start by writing what period it's in, which is going to be its energy level. So its energy level is 1. And then I'm going to say what shape it is, what shape orbital. It's the S shape, remember, because it is similar, blocks into this bit right here. And then I'm going to write how many electrons there. There are 1 here, there are 2. So I'm going to write 1, S, 2. And that is the electron configuration for helium. Okay, let's label that. So here we've got our energy level, which is our period. Here we've got our shape, which is the block, and here we've got our number of electrons in the subscript. Your coefficient needs to be normal size, your shape, normal size, and then your electrons are going to be small, and they're going to be your superscript, okay, your superscript. All right, let's give it a whirl. Let's try another one. All right, so here's what we're going to do. We're going to try another one. This time, let's try carbon. So we're going to try carbon. Okay, we're going to start on our first energy level, and as we move our pen across, we're going to write down, as we move our pen across, we're going to write down what electrons we pass. So we're going to go to the end all the way of the first period and record. We've got 1 S, and we've got 2 electrons. Again, we're going to go here. We've got 2 S, and that's the end of one row, 2 electrons. Now here we're looking for carbon. Okay, so we have 2, still in second period. We're in P though, so we have to write 2P. And then there's 1, 2. Stop at 2 because I'm at carbon. 2P, 2 electrons. So that's our electron configuration for carbon. Right? You'll notice a pattern. Let's try again. Let's go to something a little bit farther down the line. Let's go to magnesium, Mg. Okay, so I'm going to start out the same way. 1s2, 1s2, and then start over here. 2s2. You'll see we'll start to repeat. 2p, this is our p block. But this time, this time we go past the carbon, we're going to go all the way to the end of the neon. 2p, 1, 2, 3, 4, 5, 6. 2p, 6. And then to magnesium. 2, oh, nope, not 2. It's going to be 3. 1, 2, period 3. S. So let's write that. 3s. And then it's 1, 2 electrons. 3s2. And that's my electron configuration for magnesium. Okay? Let's give it another shot. Let's give it one that's a little bit more challenging. All right, let's try chlorine. We've got Cl. We've got 1s2. We've got 2s2. We've got 2p6. We've got 3s, 3s2. Write smaller. And then we've got 3p, 1, 2, 3, 4, 5. 3p5. And if you add up the electrons here, it should be the same number of electrons that chlorine will have, which is going to be 17. So I've got 2 plus 2 is 4, plus another 6 is 10, plus 2 is 12, plus 5 is 15, so it's going to be 17 electrons, and that is perfect. So what electron configuration is it's a way for us to be able, to record the electrons that we have, all right? There is a shortcut, so I'm going to show you the shortcut, and the way that happens, okay, actually let's use the same one. Let's use chlorine. The short version is called the noble gas configuration. So this is called a noble gas configuration. And if you look at it, our noble gases are here, right? So what you have to do is you have to find the noble gas that's the last one that you pass. In this case, we're going to turn around, boop, 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 boop. It's going to be the end of the row before, so neon. You're going to write neon in brackets, like this, N-E. Okay? And then you're just going to continue the electron configuration from there. So it'll be 3s2, 3p5. And what you can see is that the electron configuration, the noble gas configuration, uses a noble gas in place of writing out this long electron configuration. Okay, so this bracket stands for the electron configuration of neon. So you can just see that ending part. Okay, that's going to be very helpful for us. So I'm going to do one more. Let's do one more. All right, so the noble gas configuration of silicon right here. What we're going to do is we're going to go to the noble gas right before it, which is going to be neon, put it in brackets, and then I'm going to say 3s2, 3p2. Perfect. So you can also do this with other elements. So for example, we could do the one for fluorine, F. It just doesn't save as much shorthand, okay? So it would be helium. So we start with fluorine. It would be using helium as the noble gas. So you put helium in there. And then you would write 2s2, 2p5. All right, and that's our noble gas configuration. Awesome.